Okay, ladies and gentlemen, we have solved systems of equations by graphing. We've solved systems of equations by substitution. We solved systems of equation by combination of and elimination. But those were all systems of equations. What we're going to do now is we're going to start talking about systems of inequalities. That means it's not just the line. It means it's the greater than portion, or maybe it's the less than portion, okay? And so if we take a look right over here, we come up with y is greater than 2x minus 3. Y is greater than 2x minus 3. We can graph this. Done it before, can do it again. Let's go ahead and graph it. First things first, y equals mx plus b. Your y-intercept is -3, so we go down 1, 2, 3, and there's our point. Now we have a slope of 2 or 2 over 1. So up 1, 2 over 1. Up 1, 2 over 1. Very good. Now, the thing is, this is y is greater than. And if you'll remember, there's two things you need to be careful of when it's greater than and less than rather than or equal to and not equal to. Is your line what or what? And do you shade where or where? So is your line what or what, or is your line shading where or where? Well, in this case, the line is dotted. Whoa, that is the worst line in the history of lines. Dotted line. Now, because it says y is greater than this, that means I'm going to shade above that line. Okay. Now, if I go over here and I do the other line, I say y is less than or equal to -1/3 x plus 4. 1, 2, 3, 4. From here I go down 1 over 1, 2, 3, 4. 1, 1, 2, 3, 4. And now, because this is less than or equal to, it's actually a nice solid line. And since it's y is less than, I'm going to shade below. Now, the question becomes, what area of this graph am I interested in? Well, normally we had a solution that if two lines crossed, the solution was exactly where they touched. If they were parallel, there was no solution, or if they were right on top of each other, it was infinite number of solutions. However, in this case, we have lots of values going this way, lots of values going this way. And what we need to ask ourselves is, what is the solution to this entire system? So in essence, it's an and situation. An and situation means where is it orange and purple? Where is it orange and purple? Not here. No. Not here because it's only orange. No. Not down here because it's only purple. No. It's actually out in here. Yes, because all of this has both orange and purple shading. So that's your and situation. If for any reason they said or, you would take this because that's the and bit, but you would also take this or this because it has one or the other. But most of the time we're talking and. Now, that's all well and good. It's nothing more than graphing the lines like we always do, making sure we ask our questions, shading our lines, and now we're looking for an entire shaded area. However, if I have y equals 3 halves x plus 2, y equals 3 halves x minus 4, let's make this a less than, and let's make that a greater than or equal to. In this case, we put a couple lines on the graph, up 1, 2, and then from there we go up 1, 2, 3, 1, 2, and we draw a line. Now, because it has the equal to on it, it's solid, and because it's less than, it's shaded below. In this case, we have y is greater than or 3 halves x minus 4, 1, 2, 3, 4. Let's actually switch to purple. And there it is, and we go up 1, 2, 3 over 1, 2. 1, 2, 3 over 1, 2. And we put solid line. Now, you'll notice they're parallel, which means we shouldn't have any solutions whatsoever. But we're not just looking where the lines cross. This is y is greater than. So I'm looking for where the shadings cross. Out here it's just purple. Out here it's just orange. But in this middle area, we have purple and orange at the same time, meaning that this is the area we're interested in. So now parallel lines can have solutions because we're graphing inequalities, not just equalities. Last thing we want to talk about is if I have a situation like this. Y equals 1/2 x plus 3. Y equals 3x minus 4. And y equals 7x plus 10. Now, I have three equations in this case, and so I'm going to graph all three. First one, 1, 2, 3, up 1 over 1, 2. Oh, I'm sorry. Here we go. We need to, these are all equalities, and that's fine. We'll talk about them as equalities first. So I graph this line. The next one is 1, 2, 3, 4, but the slope is 1, 2, 3 over 1, 1, 2, 3 over 1. And so we have a situation like this. And finally, the last one is at 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the slope is 7, 1, 1, 2, 3, 4, 5, 6, 7, 1. Or down from it, 1, 2, 3, 4, 5, 6, 7, back 1. And so what we end up with is a situation with three lines on it. And what we've made is we've really kind of made a triangle. So I have, instead of just 4 areas, 1, 2, 3, 4, I have this area over here, this area over here, this one, this one, this one, this one, and the one in the middle. Now, let's assume that we have y is less than or equal to this, y is greater than or equal to this, and y is less than or equal to this one. Well, that means this first line is shaded below. The next line is shaded above. And this other line is shaded below. Now you say below, well, yes, because even though it's only slightly an angle, it's down below. What area am I interested in? The challenge becomes, where does all of it cross over? And the answer is right in here. And in a situation like this, what you're looking for is where labor costs are one requirement, personnel costs might be a different requirement in a business, and capital costs for a building, etc., are the other cost. And the question is, where's the sweet spot where the profit lies? And the answer is in the area where you have all three components, all three variables coming together. So that's graphing using inequalities, solving using inequalities. So take a look there. And I will throw another example problem or a homework problem at you here on another page.